Okay, welcome. We are here on live. We're talking today about geometry proofs and how to help your student master the geometry proofs. So this is a subject that comes up a lot, and sometimes with much frustration. We've talked to a lot of parents who some parents are very adamant we should do proofs in geometry. Some are not. Some hate it because well, they're just a little different in thinking. So anyway, if your student though struggles, I mean, they're part of geometry. If their student struggles with geometry proofs, you're certainly not alone. I didn't understand proofs when I was in high school. I mean, I don't remember a whole lot of things, but I do remember being in geometry class thinking, what are we doing? This makes no sense at all. Um, so we're going to break down kind of how we go about proofs and show you some examples, some simple, uh, a step-by-step framework. And really that's the key to proofs, is kind of a simple step-by-step framework and not getting in a hurry. And maybe the point of what we're trying to do anyway is to teach students to think about things in certain ways. So if you're here with us, help us out. We certainly trying to get the word out. We trying to help as many parents as possible, students and parents in high school math. So share if you've got a friend that's a homeschooler that's got kids in high school. Share this with them. Give us a like, um, and and let us know how we can help. So let us know in the comments here, or let us know by just sending us a support at askdrcallahan.com. And if you've ever heard the words proofs are impossible or something like that, we would love to hear what your stories are. Uh, so some of the stories are rather comical after the fact, right? After the fact, and after we understand, they're more comical. So let's talk a little bit first of all about why proofs matter. Um, a lot of people get caught up. We're used to doing math. We're used to doing adding and subtracting, dividing, decimals, and then we get into algebra and we do algebraic stuff, and we're basically, it's what we would call one abstraction from basic math, meaning instead of 1 + 2 = 3, there's 1 + X, and now we got this unknown factor in there, and we're trying to do math with the unknown. But now we start to do proofs, and I mean, geometry has a couple of things weird. One is it's doing dimensional, three-dimensional, two-dimensional, and three-dimensional, thinking about space. And for the most part, that's a win. Most students really thrive on that. They enjoy that more. They can see it. It's more tangible. It's somewhat of an applied algebra. But when it comes to proofs, of logically thinking through things, that's a different thing. It's different, and it's different for most students, but that's why we teach it. That's why it's part of here. Logical reasoning and critical thinking skills are some of the biggest things I hear about from employers. Now, I'm not talking about taking the SAT, ACT, college. I mean, it's certainly important there. But when I talk to employers who are hiring everything from business people to engineers, critical thinking is a big, if your job is paying anything, if you're not slapping something on a burger or something. And I might even suggest there's some critical thinking that goes on there, at least maybe we hope. But for most jobs out there, critical thinking, logical reasoning is important. And the more you can do that, the better off you are. And so structured problem solving is a skill we use in math. So when I think about proofs, that's what I want you to think about, is structured problem solving. We use this in math, of course, but math is a language. People get caught up in math. Math is really a language, just like English is a language. And by understanding English, we can read and write and communicate and read the Bible and read and write our own stuff, right? So math is the language that God created the universe, and there's a language behind it. And did God create math? Yes, apparently so. Because if you've done any amount of science or any amount of study or engineering, you see things in math that it doesn't make sense that they would be this way, right? It's certainly not random. And even what we think of as random is mathematical. So, but these skills are useful. And what it is, that's all we're doing is structured problem solving. And the reason it's structured is because it's a little bit bigger than you can do in your head. And that's where most students start to get hung up when they transition from K through 6, a grade math or whatever that is, and they get into the high school math. And now we're starting to be structured. The problems are multi-step, and that's where they get a hang up. And so proofs is the answer to that problem. Thinking about the proofs and how do you do proofs are the answer. So also, you might want to look at where does this order come from? Because proofs are looking at the order. They're looking for order. 1 Corinthians tells us, but all things should be done decently and in order. Okay. Whatever that means to you, right? That's just said straight out of the Bible. It's not me. Geometry proofs teach us the value of order. And they're teaching our mind to think in order. And we always hear, because of this 1 Corinthians and other places scripturally, God is a God of order. So we are trying to train logical reasoning, which it means structured, step by step, having some order, having some process in your brain. And it's when a student, now we do this at different ages, right? And you will see students start to do this, or kids start to do this even at a young age. They'll start to organize things like their Legos and things. But when we get into high school, the organization gets a little more complex, right? So I would, we'll jump into that here, but we're going to look at proofs and kind of a framework. So, but that's why proofs are going to show up. We're not always going to say, prove this. We're not always going to say, this is a proof. It's not always going to be a 2-column proof, at least written down, but we are constantly having to prove stuff. Watch social media. Watch as people would say, the misinformation that is out there, whether it is or not. Figuring out, is misinformation and misinformation. Now, we're not even talking about math, X, Y's, anything else. Just looking at the world, looking at the data that we have to process every day. Is this true or is this false? How do I logically go across around that? So I will take a simple example. You see an image posted on some kind of social media that shows people doing something that they said they didn't. Politicians. And you look at the image and you're like, is this true? Were they really there? Did they really do this? And then right now, this is the case. Right now, you can look at the image and look for artifacts. And right now, the artifacts are often easy if they're AI generated. Like the girl has 10 fingers on one hand, and weird stuff like that the AI engines mess up today. But that thinking of, oh, well, that's not really true. This picture is made up by AI or something else. And you can look at this and see that. That's logical proof thinking. And you are just taking one step at a time to say, well, because that's not true, then this media story or this image is not true. And so therefore I'm going to doubt, is the rest of this true, right? You've now, it's a courtroom case, right? This is very much the same process. All right, so let's walk through a framework on how you do proofs, kind of a step-by-step framework. And I'm going to do this, and I'm going to show you a quick example. So let's just talk about it, and then we'll do I'm going to show you a simple example off of a website. So a step-by-step proof. Now, when I'm saying that, I'm going to refer back to geometry right now for a minute. Um, is understand the given information. I guess it doesn't matter whether I'm talking about geometry or not, but understand the given information. When we talk about a proof, usually in mathematics or in science, it's like, um, this is our situation. Prove to me this happened. Again, think about a courtroom case, right? Lawyers are there. This is a situation. We're trying to prove that he or she is guilty of this or not. But here's the background. Here are the given facts that both sides and the judge and everybody agree on, these given facts. And we're going to try to walk from the given facts to prove or disprove a situation. That's what a proof is. And it's got to be very logical and instead of emotional. So we're going to start with understanding the given information. That's number one. Number two, we're going to identify what needs to be proven. Now, we haven't done anything yet except read the problem. All right, so let me pull up real quick if I can find it. Well, let me do that. No, let me do it now. Let me pull up real quick this example if I can make this work for me correctly. Let me share a screen. Share an entire screen. Is that the correct screen? Never know what's happening here. Okay, that looks like the right thing. That right there I am showing you is straight out of Harold Jacobs' geometry textbook, page 96, chapter 3. And what we see here is he's talking about a pool table. Somebody's playing pool, and what he's trying to point out, and we won't bother reading the problem, but is if you shoot a pool table and it hits the bumper on the other side of the pool table, and it's going to bounce off at the same angle, right? And then he says, and that's kind of what he's showing. He's got a figure drawing this right here. And so that what he's trying to do here is he's giving us some information. And he said, in this view of a pool table, the cue ball is shown banking off the lower cushion. So now he gives this in mathematical terms. So that's kind of the real world in mathematical. When a pool ball banks off the cushion, the angle it forms from the path of the cushion are equal. So he's saying from point A to point P down here to point B, those two angles, angle 1 and angle 2, are equal. If you don't understand, I mean, don't worry about the details here. I'm just saying this is what he's telling you. Is then he's saying, for example, this is what happens. Okay, so he's giving you this information. All of that is given. And now he says up here at the top, he's saying, which you can't see because I took a picture of it and it's curved a little bit. He's saying it's easy to prove from these facts that angle 3 and angle 4 must equal. Now, I'm not going to do that. This is a little more involved than I would want it to be. But for this video anyway, notice he gives us all of this information, and now he's saying prove this. So he's done two things: is what's given and what I want you to prove. Prove that angle 3 and angle 4 are equal. So this is angle 3 and angle 4. I want you to prove them. And so that's what we're going to do. For the first thing we want to do is just get our head around what is given, what is being asked for. And by the way, this goes beyond a geometry proof. When we talk to or we are supporting customers and students, quite often they will email us, and that's the problem they have. It's not that their math was wrong. They're not doing anything wrong, but they didn't understand what was asked of them. So it's unclear. So understand the given information and identify what needs to be proven. And we see this all the time in all of our courses, that students are off working another problem. They don't mean to be, but they forgot what they're trying to achieve. So understand the given information, identify what needs to be proven. And so this is kind of like read and understand, right? That's how, if I need to take a pen to paper and draw it and write it out myself, which is maybe preferable, read and understand before you start doing the math. And oftentimes that's exactly what the problem is. We get in a hurry and we start doing things without reading and understanding. So this third thing is planning the proof. And then it's just saying, what steps do I think I have to go through? You can kind of logically, do this. Let me go back to this screen I was on, if I could get there again. How do I get there? Oh, I'm not doing that the way I want to do it. There we go. Okay, you should see that screen again. Is since he is saying, given from these facts, because he gives us another ball here, C and D, he gives us these facts, and so what you're doing is you've got these angles, and we can kind of look at and say, okay, where I'm trying to get to is that from these facts, prove that 3 and 4 must equal. So I'm trying to prove these two angles down here, 3 and 4 are equal. So I can kind of see, well, where it looks like, okay, these other two angles are equal. And so there's some relationship between all these angles. And maybe if I add and subtract them out, I will get to the desired result. Now, usually you have some thought of where you're trying to go. You can, the trick about geometry proofs is oftentimes we can look at it and say, well, duh, that's obviously the case, which is true a lot of times. That is very true a lot of times, except you don't want to trust that. And what do I mean by that? Is if you are building a home and you have had a builder pour a slab for you, and he stands back and he says, looks pretty level to me. You don't want to trust that, right? If I know most of us, we're going to be out there with a level, checking it every particular angle. This is off. This needs to be filled in. This is not accurate, because we know when we build on that improper, that foundation that is not poured properly, bad news happens. We don't trust that looks right, and that's exactly why we shouldn't trust our logic. Sometimes our internal logic that looks right is not always right. So that's what we're looking out for. That's what the reasoning we're trying to say is, how do we know? Where we take a trusted instrument such as a level or a laser level, and we build a framework and we trust it, and we've verified it with the known device. And I mean, it's the way a builder, if you watch them do that, they have a known device that shows level, they build a frame, they build a structure to pour the concrete in, and they verify that with a known device. And now they've proven that their structure is level, and now they pour the concrete, and they may even do other stuff to prove that everything is accurate. So that's what we're doing. That is what we are trying to do here with geometry. All right, let's go back. No, I just have to figure out. I have so many screens open. Okay, so that's planning the proof. So we're understanding, understanding what's given, identifying the information, planning it out, and then just build the steps logically and write each steps down with a reason. So I'll show you that in just a minute, and review and double check your work. Okay, so we can say it's 5 steps, maybe it's 4 steps, and so let me go through a example here that's from a website. Let's see if I can show this again. There we go. All right, let me get rid of this guy. All right, so here is a website. Is this from, I don't know, I'm not affiliated with Tutor Portland. It looks like it's a tutoring service. Tutor Portland looks like it's a tutor service in Portland, if I had to guess. So he's showing us an example here of a 2-column proof. And so this is a simple proof. He's saying it's given that C and A, that's an angle C over here, and angle A over here, and he's also got an angle B over here. And we see they're just two angles. I mean, they're three different angles. It's given, meaning I'm telling you this is fact, that C and A are complementary. Okay, if you don't know what complementary means, it says right up here. Complementary means when you add C and A together, you get 90. Such C might be 30 degrees, A would be 60 degrees, and you get a 90-degree angle. Now, it doesn't look that way. It looks like they're equal. So they could be 45 and 45. We're not doing look here, right? We're not saying that looks level. We're saying if I add the two of these together, they will make 90 degrees. It doesn't matter what angle they are. So that's what he's telling us. He's saying if C, and it's given that C and A are complementary. So that's all we know. Angle C plus angle A equals 90. And he's telling us that it equals 90. It's also given that B and C, so the angle B over here and angle C are complementary. So if I add C and I add B together, they also equal 90 by definition. Now, all of that information is given, proven in a court of law. Right? So now, and he's got it written out here, and this is the way we usually do it. Angle A and angle C are complementary. Now, you might want to sit here and say in your mind, well, A plus C equals 90. Don't get there yet. This is the step-by-step thing. Remember, what is given? Don't add to what is given. If you do this in a courtroom of law, you're going to get an objection from the other side. You cannot add to that information. You got to prove. It sounds a little ridiculous, but walk with me. All I'm given is it's given that A and C are complementary. Don't add any more information. Boom, I wrote that. And then it's given that B and C are complementary. That this little thing where he says meaning they add together is equals 90, you don't usually get that in a proof. So just write down what is given. So that's the step one, is be clear. And this is one great way to be clear, is take a sheet of paper and write down what is given and make sure you have written down only the given information and not anything else. Draw you some pictures there as you need. Then what he says here is prove angle A, and we're going to just call it equal. Angle A is equal to angle B. So that's all he's asking for. So now I'm clear on the first thing I've read, and I'm clear in my mind. You're saying these two together are complementary, and these other two together are complementary. And what I want to prove is that these, A and B are equal. Or congruent is the definition of that little weird thing, but we're going to just call that equal for right now. So that's so all this time I'm trying to make sure I know what's given and what's proved, what I want to prove. Now this isn't what your student would be doing all the time, going through all this thing, but I'm just saying this is the slow it down, make sure, and then jump in. And you can kind of logically sit there. I mean, probably if you're watching this and you're thinking about this at all, you're saying, well, clearly, if those two are equal, then those two are equal, then those two have to be equal. I mean, it's obvious, right? It's obvious. And if you're not paying attention enough and you're like, it's not obvious, well, it's one of those things. It's obvious. It's like the builder looking back. It's obvious. It's level. That looks like it's true. So, but what we want to do is walk step by step. And so the way we're going to do that is we start with a statement that are given. And this is a weird thing to do in a proof, but this is what they do. And this, by the way, is what we would call a two-column proof, where on the left-hand side we make the statement, on the right-hand side we make the reasons. A lot of people criticize Harold Jacobs because he doesn't do column proofs, because he doesn't make them look this way. But it's the same thing. They don't have to be in columns, but it's a statement and a reason. So what the first statement is, angle A and angle C are complementary, and angle B and angle C are complementary. How do we know that? What's the reason? It's given to us. And usually that's where we start. Okay. Now we're going to say angle A plus angle C is equal to 90. And angle B plus angle C is equal to 90. Now, how do we know that? It's the definition of complementary angles, right? Now, a lot of you would say you would skip down to step 2 that I'm on now. It says step 1 on all of them for some reason, but you would step down to this, and that's where you make the mistake. You made an assumption. You got to walk me through step by step through the process. How do we know this? It's the definition. Okay, so now we know angle A plus angle C is equal to angle B plus angle C. So I took out the 90s, right? So this is equal to 90 and this is equal to 90. So A plus C is equal to B plus C. How do I know that? It's called a transitive property. I won't get into that. Or it's called substitution, meaning that they're both things are equal to 90. So there's a couple different, and that's true a lot of times in geometry. Your reasons could be different, but there's a reason. Right, and then we're going to say now that means angle A is equal to angle B. So angle A is equal to angle B. How do we know that? I subtracted C from both sides. I did a little algebra, right? So that's subtraction. And then it's going to say angle A, and there's the weird little equal sign, is a congruent to angle B. And that's the definition of congruent. We won't go into that, but basically it means if they're equal, they're congruent. So now all that seems like a lot of stuff to say to do a proof. And if you're a student, and like me, when I was doing them, I like, well, this is stupid. Why am I writing all this stupid, painstaking steps down? I can jump way past this and go way faster. That's not the point. The point is to teach you logical, critical thinking, because you can do that here. You can't do that in real life. You can't do that in real science, and you can't do that when the math gets harder. You have to walk through. And there are going to be some problems in geometry or in algebra 2 and trig or calculus that you're going to say, I can't get from here to there. I kind of got to get my pencil and pen out and see if I can't get there and figure out the reasons. So it's painstaking. But I also would liken this to cooking a little bit. And I don't cook, but I've been told enough about certain things about cooking. When you are cooking, and when many of you would cook a meal and you would throw in salt or throw in pepper or add this much meat, and for many of you, I would ask you, well, how much meat? And you would say about, right? We would throw about this much salt, about a handful, about this, and I'm like, well, that doesn't mean anything. Like, what is it? A pinch of salt. I still don't know what a pinch of salt is, but it's a guess, and it's more than a hand. I mean, it's less than a handful, and I don't know what it is, but it's some estimated measurement, right? That everybody that cooks a lot understands. It's not precise, and it's not meant to be precise. So my wife will often say, salt it or pepper to taste, which I don't know what that means when you haven't cooked it yet. But anyway, it's a little bit of it's the skill. Again, it's the contractor saying that looks about level for what we're doing. That's perfect. If I'm building, a duck blind to go duck hunting, about level's fine. If I'm building a 2-story home, about level is not fine. So it depends on what you're doing. So point being, if you're cooking a meal, you can do that. If you're baking, I'm told that measurements need to be more precise. A tablespoon, you start talking about tablespoons and cups and more precision measurements, because if you don't get it precise, you get pies that you made for Christmas that don't look like the pie you thought they were going to look like. They don't gel, or the candy doesn't set up correctly because they weren't precise. They are that's more of, so baking is more of what we would call chemistry, and cooking is, well, cooking is just cooking. So when we think about chemistry, we're thinking about precise measurements, and it's precision, and it's a process, and it matters. And this is what we are trying to teach with geometry, that precision and preciseness matters. Maybe not on the problems we're doing in front of us, but it's going to matter so often. We actually have a good friend that's a chemist, and that does drug development, and he was telling us the other day they blew up some stuff in their lab, and it was like because the test tubes or the test equipment that they were using had it didn't have water in it, but it had there must have been some leftover, how did he word it, leftover moisture, and when they put this in there, after a few minutes it exploded and caused all kinds of chaos. Precision matters, and so the next time they did that, they went to great lengths to make sure there was no moisture. All right, so that's science. This is what we're talking about here. It's the language we're dealing with. All right, so this is again. Let me walk through the process. Is understanding the given, and if you can understand, if your student will understand the given information, what is being given, if they will get super clear on what they need to prove, and they will walk through the steps very carefully. Maybe they feel like stupidly carefully. That's fine. Then they'll get it. And once they get it, they'll be in motion, and they'll be doing this. The problems that people have with this is they skip steps, or they don't use their theorems correctly. And you're going to find in Harold Jacobs' book, if you're using it, the way he does proofs is very much like it's not this this boring 2-column method. He's going to do more Q&A things, like the example I just showed you. So there's proofs all through there. You may not always recognize them as proofs. So, okay. So this is it. This is a big problem. This is a problem that we encounter a lot. It's not that hard. As a matter of fact, usually the proofs are pretty easy in geometry, and anything that's the real world problems that looks like, pictures of real stuff like pool cues and billiard tables are usually pretty easy. They're not extremely complex math. All right, so if you're looking for some help though with geometry, we have a course, and we have a course in algebra, a whole course in Harold Jacobs geometry that are preparing our students for the well, it's high school math. It's 2 of your high school maths. If you're college prep, it's 2 that's going to be expected of you, and 2 that will lead up. If you're doing the ACT, these are expected, or the SAT. It's a moving target. But right now, also many of you are thinking toward ACTs and all for this year, next year. The thing that you want to do to prepare and do better on the ACT test for the math section is just do more math. So Algebra 2-ish trig is where a lot of our customers and students will jump into, because it really builds upon these things so you help understand them more. So as a matter of fact, let's see if I'm telling you this correctly. We have a yes, we have a sale down in the comments below. We have a sale right now going on for Algebra 2 and trig and our calculus, everything you need products. Now, anybody heading toward college, or they just want to be prepared at that level, that has anything to do with science, anything to do with engineering, then these are probably the courses that you're going to want. And I'll even throw in business. A lot of business schools these days are requiring some level of calculus. But certainly in the sciences, you need the mathematics background. And what a lot of parents are doing is, I don't know where Johnny and Susie are going, but let's prepare them kind of for the worst or the most challenging scenario. So there's these two courses. We've got them on sale. I would tell you what that was for, but I don't know right now. But you can go to the link and see what those things are. All of the, so what you're going to see here if you, in doing geometry proofs, and some people think, well, that's just in geometry. When you get to Algebra 2 or trig, you will see a lot of algebraic proofs. Now we're going to be combining geometry and algebra. You get into trigonometry, and in trigonometry, we have what's called trig identities that I won't bore you with, but they're just essentially proofs that you're doing all the time. But you're always doing proofs, and all of your advanced mathematics, all of your advanced science, all of your life, you're doing proofs. Such as the customer who's sitting there watching their foundation be poured. You get seriously proof ready and seriously analytical when you are spending your money, as we probably should. As we would say, God is a God of order, and we should, at least when big decisions are, we should think in order. All right, that is it for today. We've got the comments over there. In the comments with the two links on. It looks like they're 30% off of the packages. If I'm reading that right, 30% off of the packages for right now. And I think that is the rest of the month. All right. So we will be back here. Thank you for joining us. Thank you for paying attention and being here with us. We will be back here next Thursday at 3 o'clock. Thank you.